Hello everyone, this is a story of how me and my friends kind of made a new physics equation in freefall. So for some context, I was doing my capstone project, which I have a video on, link will be in the description, hopefully if I don't forget. Basically, I wanted to find out how long it took for a bomb to drop from Pearl Harbor when the Japanese attacked. And now, these bombs that were dropped at 3,000 meters, so air resistance was going to play some role in the timing of the bomb drops. But so far, nothing in my school's physics curriculum nor the AP physics curriculum up to AP Physics 2 have talked much about air resistance and how you're actually supposed to use it in like kinematics and forces. So I kind of deviated from the normal kinematics equations and I went and wanted to make my own equation to help me answer the question of how long would it take for a bomb to fall onto one of the ships. Now, in order to do this, we needed two integrations because we're going to be integrating Newton's second law, F net equals ma. And after only integrating it 2 times, do you start to get distance? Okay, so first of all, F net equals ma, that is pretty self-explanatory, and Fg is mg, that is also pretty self-explanatory. This is not very self-explanatory. This is the equation for drag. Rho here is density of the air, v squared is the velocity of the object that is traveling through the air, and then c is the drag coefficient, and a is the area of drag. Now you can see here there's a lot of more variables, and that makes it a bit of a headache to look at. But really, the only variable here that's actually changing much is the v squared, because the area of drag shouldn't change much, and neither should the coefficient of drag, if they even change at all. Now, the density, the air density, it does change, but I don't think it's going to have that much of a difference on the equation. And since we're going to be integrating this with respect to dt later, this change of rho I don't think is really going to affect anything. So we formulated the Newton's second law equation here, where up is positive, down is negative. So the drag force is trying to make the bomb go, trying to slow it down by providing an upwards force, and gravity is trying to pull the bomb down. So we just wrote B is equal to rho CD over 2. So that makes this a lot more pleasing to look at than this monstrosity of up here. Now you know, or may not know, but I'm telling you now, that acceleration is dv dt, because it's change of velocity over change of time. That's the basic definition of acceleration. Now, we're here, and we were stuck for a while because we didn't know what to do. We tried to turn ma into mdx, d2x, and then dt, d2t. Okay, I can't English, but basically we try to turn acceleration into the second derivative, the derivative of distance, and we tried to turn velocity into the first derivative of distance, but that didn't turn out to work so well, so we kind of wasted like an hour trying to integrate that thing. So we just made it a bit simpler. We made dv here and dt here, and we did not touch this velocity, unlike last time where we changed this into dx dt. Now, we're going to do separation of variables, and by the way, this is not my work, this is my friend's work, but I don't know if he wants to be mentioned or not, so I'm going to keep him anonymous. And there's other people that also helped, but I don't know if they want to appear in the video, so I'm just going to keep it anonymous for now. We're going to conduct separation of variables. Basically, why this matters is because m here is a constant, like the mass of the bomb is not. It's not just going to magically gain 20 pounds of explosives mid-air. That doesn't happen. So we have separated on one side, and on this side we have dv and then v. These two variables, they match. So now we can integrate both sides, and we essentially integrate here first because this is the easiest part. So we get Tm, and there is some switching around here and reorganizing the equation. And then we get to this point here. Now, this was the breaking point, because first time that we stumbled upon here, we didn't know how you could integrate this, because what in the world is this? This is an integral of 1 over something that's a constant minus a variable squared, and a dv. Now, that's where this chart right here comes into handy. So this is a pretty standard integral formula sheet that pretty much every calc student should have seen something similar like this, I'm guessing. Yeah, so if you look at this, you'll notice that there are these 3 equations down here that are highlighted in gray. And the reason is because when I took AP Calculus BC with my teacher, he said, you don't have to worry about these equations at all. So guess what I did? I didn't worry about the equations. But now, as it turns out, I was searching through this formula sheet with my other friend who didn't write this up, and we were trying to see if anything in here actually fit whatever monstrosity this is. And as you can probably tell, this one fit right here, the first of the 3 gray equations. So it actually fits perfectly well, but we just have to redefine a, because a squared is obviously not, well, a squared is mg over b, but a is not mg over b. A would have to be the root of mg over b. So when we follow this format, we get to here. And that is basically how we actually push through the first integration. And we got rid of acceleration in the equation. So I think now we are around like here-ish, somewhere here. And then there's just a bunch more switching around terms, some simple like log exponential stuff here. And as we go on, we're gonna now begin to integrate it a second time, which is what's happening here on this page. So eventually, my friend got to simplify whatever we integrated from this equation into this here, and then we integrated that again, because that's how you get from velocity to distance. Now, he had to use some partial fractions. I forgot about partial fractions because I learned them like a year ago and I never used them after that, so to be frank, I'm not quite sure how this works. But I'm showing you the steps here, so if you want to go ahead and check this out, you can, and if you think there's any error, just tell me. So finally, we got to this equation down here. Now, this looks a bit unruly, I must say so myself, but it becomes even more unruly because if you remember, the b in this equation is actually not b. B actually means rho coefficient of drag, area of drag, over 2. So what that means is that once we expand out b to have the proper variables, we got an equation that looks like this. Now what you do have to note here is that I believe, actually no, not I believe, that I know that this square root is actually a part of the exponent. So this is e to the exponent of negative absolute value of time, and then the square root of this whole monstrosity. And the plus 1, I believe, is not in the exponent. And also we have to expand the b that is here as well as in the root here. So since b is in the denominator, we just flip the term. Now when we compare this to Wikipedia's equation, which is this one right here, we find some similarities, such as the 2 multiplied by mass, over the common variables of area, coefficient, and air density. Now, I obviously could have, I think it's called rationalize this denominator to make this one big fraction, but I really didn't want to do that just because I wanted to keep it simple. Yeah, because if you multiply this whole thing by root AC rho, this term up here would get more complicated to be AC rho, and I didn't really want that. And one other commonality is that you can see that there is the ln I have here and the ln that I have here. Now, the unique thing about the Wikipedia equation is that it has hyperbolic cosine, which I didn't understand when we actually did this thing, because I don't think any of us had any knowledge about hyperbolic trig. So obviously we couldn't integrate into something that we didn't understand, nor did we know of. So this was the best equation that we had to come up with. Now this equation actually, these two equations actually match each other when I plug in the variables and use them to find out the Pearl Harbor bomb drop time. Maybe I'll link that video in below too if I don't forget. But I actually sent out this equation to professors from 3 different universities, and only 3 of them replied back. 2 of them kind of confirmed my equation, and then the other one kind of provided like this little chart that was a little bit mistaken because of this right here. I think he thought that this was multiplied by e and not actually in the exponent of e. So yeah, so he provided kind of a faulty data graph, but you know, it's not his fault. I genuinely appreciate him for trying to help me out here. So yeah, I think this is basic confirmation from the 2 professors, Wikipedia and Desmos, that this equation looks correct. Yeah, that's basically it.